All right, how could we factor that as a difference of squares? All right, think about it. Think about x squared minus 36. How do we factor that? Yeah, x plus 6, x minus 6. Okay, so what about cosine to the 4th minus 1? Cosine squared x minus 1 times, what else? Cosine squared x plus 1. Okay, so that's usually going to give you something to factor there. Now, the other strategy here, so we're actually going to do 3 different strategies today that all work together. So factoring, and now this next one here, it's to simplify also, is called splitting. Okay, now this says right here, splitting is only when you have a single term in your denominator. Okay, not when you have multiple terms in the denominator. So let me give you an example of this one without using trig. Let me give you an example like with the quadratic formula. All right. So for instance, let's say we had something like 5 plus or minus 7 square root of 3 over 10. Okay, and it really has a lot to do with the factoring strategy here too. Okay. In the factoring strategy and the splitting strategy, when it comes to simplifying, it's kind of like this. I get this reaction. I really, really want to cancel something out, but because my operation is not multiplication, I can't. All right. So what do you think I really want to cancel out right there? The 5 and the 10, right? But we know better, right? That's something that we do like in the 11th grade, when we weren't too sharp on things. First time we saw the quadratic formula, maybe. Okay, but we know we can't cancel that out. So when you want to cancel stuff out but can, I want you to think of 2 strategies. One is factoring, okay, factoring out a common factor maybe to get something to cancel. The other, when you have a single term in the denominator, is splitting. Okay, so splitting means that I'm going to take these 2 fractions. Instead of writing, or these 2 terms, instead of writing as one big fraction, we can write it as 2 smaller fractions. So when we split this, we could get 5/10 plus or minus 7 square root of 3 over 10. All right, does that make sense there? All right. Now, so now can I reduce the 5/10? Is it legal now? Yeah, because it's now an individual or just a single fraction. So now I could write that as 1/2 plus and then 7 square root of 3 over 10. Okay, so now we talk about factoring and splitting here so that we can simplify. Now, let's look at a lot of examples here today. Okay, this is just those strategies, and we'll get to one more here that's really the main one. All right, let's look at this problem. Now, I actually think we've done one like this before. Okay, you just didn't really know about those strategies yet. So let's see what we can spot in this one. Kind of got it underlined. Sine x minus sine x times cosine squared x. So what can we do there? Right, factor out of sine x. Okay, so let's see where this will hit us. All right, so sine x times, so we're getting out a common factor, right, 1 minus cosine squared x. Okay, now, after we do that, now let's see what we can spot there. I see a 1 and I see a square, so I should think Pythagorean identity. All right, so now let's think about our Pythagorean identity with cosine squared. What we know, sine squared plus cosine squared equals 1. So 1 minus cosine squared would be sine squared. Okay, so instead of writing 1 minus cosine squared here, I'm going to write that as sine squared. Now, let's see if you guys can simplify that now. So what's sine times sine squared going to give me? Sine to the 3rd. Yeah, I mean, think about it. Does it make sense? Okay. It would be sine, I'd say sine cubed x. Now, let's look at another one where we could use some factoring here. All right, let's see if you can spot this one. All right, they're to the fourth power. So that should tell you something there. Sine to the fourth x minus cosine to the fourth x. Difference of squares, isn't it? Okay, so now let's factor that as a difference of squares real quick. So it would be sine squared x. All right, what else? Minus, all right, cosine squared x times sine squared x plus cosine squared x. Okay, and this is all over cosine squared x. Okay, now I've got a bunch of square ones, don't I? All right, you see anything in that anywhere? This ought to smack you in the face. If it doesn't, I will. No, I'm not going to do that. All right, what? Somebody said something about 1. Sine squared plus cosine squared is 1. Hello? Okay, so this is just 1, isn't it? All right, and then 1 times that would just be that, wouldn't it? All right, so it kind of gets rid of one of those for you. So you got sine squared x minus cosine squared x over cosine squared x. Okay, now, so I'm seeing something here. I see those cosine squared x, and I'm like, man, I would really love to cancel those out. But you can't. So we can, all right, somebody said it, split it. Okay, and let's think about what's really telling me to split here is the denominator. Notice it's only a single term, isn't it? Okay, that's a really good hint to sometimes split here. So this would leave me with sine squared x over cosine squared x minus cosine squared x over cosine squared x. Okay, now can I do some canceling or reducing here? Yeah, the cosine over squared over the cosine squared would be just 1. Now, what about sine squared over cosine squared? Tangent squared. Now, so now I'm seeing a square and a 1. So what am I thinking about now? Pythagorean identity. Okay, but there's a problem with that. I think it works out better in your problems, but this problem it doesn't work out as nice. What's our Pythagorean identity with tangent squared and 1? It's what tangent squared plus 1 is secant squared. Okay, so if that was plus 1, we could say secant squared, couldn't we? All right, that's it. That's all we can do there. Okay, simple as we can get it. But if that did turn out to plus 1, and I think the one that you're going to work does turn out nicer. All right, now let's look at the final strategy here for today. All right, complex rational expressions. Okay, so let's look at this from an algebraic standpoint first, and then we'll kind of look at some examples with the trig. All right, so over here on the right side, let's write a complex rational expression. So something like this, maybe like 2 over x plus 3 over, say, let's do 5 over x plus, let's say 5 over 2x plus 7. Okay. So remember the idea of complex means we have fractions within fractions. All right? And we kind of got some of these doing half angles. What's the strategy here to like clean them up and simplify them? Multiply by the common denominator.
Is that a 2x?
Okay. Yeah, that's 2x down there. All right. So now, what would be my common denominator then? Not quite x. 2x. All right. So I'm going to multiply everything here by 2x. And when we say everything, we mean everything, right? This over here too. And so this should get rid of all the little fractions, and we'll have a big fraction left over. All right, so now, what's going to happen here with the x and the 2x right there? The x's cancel out, and so that would leave me with 2 times 2, which is 4. All All right, now right here, 3 times 2x would be 6x. Okay, right here the 2x's would cancel, so that would just leave me with 5. Okay, and then 7 times 2x would be 14x. Okay, all right, you remember that idea, that algebra idea there? Now, what we're going to do is we're going to take that idea of multiplying everything by the common denominator and just do it with trig. Okay, now, you'll see them kind of come out as we do them. So, one thing about the complex rational expression ones, they don't happen until you get to like the second or the third step into the problem. Now, let's address it with our strategies here. All right, so I see something in there that you should recognize. 1 minus sine squared, cosine squared. Okay, so we'll get cotangent x over cosine squared x. Now, after that, you've got 1 square, you don't have a 1 anymore, and then the other function's not squared. All right, so what happens here, and this is, coming back to another strategy. If you don't know what to do, go back to the first strategy I taught you. What's that first strategy? Yeah, change everything to sine and cosine. Okay, so let's do that. So we can change cotangent to cosine x over sine x. Now, so when you get to that point where you change everything to sine and cosine, a lot of times what happens is you have a complex fraction. That is a complex fraction, isn't it? Okay. Now, the truth is, we could really do this one by multiplying by the reciprocal of cosine, and that would work. Okay, but let's use the strategy like we did over here. Let's multiply by that common denominator. Now, when we say common denominator, notice we're not considering this cosine down here, this cosine squared, as a denominator. What's its denominator? 1. Okay, so what would be my common denominator to multiply by here be? There's only one denominator there. Sine x. So I'm going to multiply the numerator and the denominator by sine x. Now, do y'all see what I'm talking about? Okay. So we're going to multiply both by sine x here. Okay, now, what's going to happen in the numerator when I do that? Yeah, they'll cancel out. So that'll just leave me with cosine x over. Now, my denominator, I'll have cosine squared x times sine x. Now, let's see if y'all can figure out what to do from there. Can we cancel? All right. Can we cancel the cosine x with the cosine squared x? Okay. Is that legal? Yeah. Because what's happening down here? You're multiplying. Remember, we can cancel out as long as the operation's multiplication. Now, they're totally not going to cancel out, are they? The cosine squared is just going to go down to cosine. So I'm going to use this little nifty trick. I'm going to cancel out cosine. And down here, what can I do? Just cancel out the 2. Does that make sense? So now, what's left in the numerator? 1. All right, so we got 1 times, and we're left with cosine x times sine x. Now, the next thing's hard to do because you have 2 of them right there, and you're not used to writing with 2 of them like that. But y'all think, how do we simplify or write 1 over cosine x in a simpler form so it's lesser ink or lesser pencil that I'm using? What's 1 over cosine? Secant. And what's 1 over sine? Cosecant. So we could write this as secant x times cosecant x. Now, just to kind of give you a hint, I think one of your problems that you're going to do, you're going to wind up maybe with a 2 in the numerator. So what if I had a 2 in the numerator? Then my answer would just be 2 secant x cosecant x. Okay, if there was any other number, that number would just throw in the front right here. All right, let's look at some more of these. I really like these. These aren't really as bad as they look. To me, tomorrow we're going to get some that are really, really difficult. Okay, tomorrow's like the hardest day here. All right, let's look at this one. All right, now, let's talk about some strategies. Crystal, look up. All right, so give me something that's missing that would really help their squares, right? So if I had some squares on my tangent and my cotangent or my secant up there and some 1s, I might could do something with the Pythagorean identity, but I don't have that. So I don't really see anything that jumps out and bites me here. So what happens when I can't think of anything to do? Change everything to sine and cosine. All right, let's try that. So let's see. Secant. Tell me what to write. All right, 1 over cosine. All right. And then on the bottom, tangent. Sine over cosine. All right. And then cotangent. Cosine over sine. Remember, changing everything to sine and cosine. Okay. Now, kind of looks like when you do that, you make matters worse, don't you? But look what we made it into. What do we call that? Complex fraction, okay, or complex fractional expression. All right. Now, we know how to clean them up, don't we? We just multiply by the common denominator. All right. So, y'all look at the denominators. You got a cosine, you got another cosine, then you got a sine. So, what would my common denominator be? Cosine times sine. All right. So, we're going to multiply every term by cosine x, sine x. Now, when we do this, it's going to get much nicer. So, sometimes, you ever heard, it's going to get worse before it gets better? That's what happens here. It gets worse before it gets better with your complex one here. So, you got cosine x, sine x, got to squeeze it in right there. All right, same thing over here. Cosine x, sine x. All right, now, we should get some stuff to go away. Alright, so what will happen here? Cosines cancel out. So it's just, is that 1 over sine or just sine? Just sine. Okay, because that's the numerator right there. Alright, in my denominator. Alright, tell me what to do there.
Cancel out cosine.
Right, alright, so cancel out cosines. That would leave me with the sine times a sine, which is sine squared. Okay. Oh, there's our square that we were talking about a while ago. Okay. All right. And then on my other one, the sine x cancels out. All right. So what would that leave me with then? Cosine squared. And now, slapping you in the face. Sine squared plus cosine squared is what? 1. So this is just sine x. Imagine all that, and it's just sine x. That's all it is. Okay, goes down to that. All right. Now, did you see the complex idea here? When you run out of stuff to do, well, change everything to sine and cosine. And usually when that happens, you get a complex fraction. Well, we know how to use algebra to clear out those complex fractions. All right, talking about like right here. All right, this right here. Sine squared plus cosine squared, that's a Pythagorean identity. That's just 1. Right? Now, is it really necessary to write like right here over 1? No. Okay. If it's in the numerator, then we have to write that 1, but not in the denominator. All right, let's try this. Somebody want to try this one? You come up here and write on it? Anybody? Chicken? Okay, I'll do it. Now, let's look. All right, again, I got some 1s, but what's missing? Squares. Okay, so maybe if one of those was cotangent squared or tangent squared, I'm looking at a Pythagorean identity, but no. Okay, they're not squared. So, gosh, I can't think of anything else to do, so I'll go to the Waffle House. No. What, change everything to sine and cosine. That's usually my thing when I can't figure out what to do. Just go to the Waffle House. All right, for supper. All right, so 1 plus, all right, cotangent x. Help me out. All right, cosine x over sine x. All right, over 1 plus sine x over cosine x. All right, now what are we looking at? We made it worse. It's a complex fraction, right? Got to make it worse before it can get better. Now, we can multiply, though, by the common denominator. All right, so y'all tell me, what's the common denominator going to be? Yeah, sine x, cosine x, same thing as last time. All right, now I'm going to make a mistake though. Okay, let's see if you can kind of pick up what I'm doing wrong when I do this. So we said sine x, cosine x, and I'm going to multiply it by. So sine x times cosine x. Alright, right. I need to do it to those ones too, don't I? Okay, so you got to do it by every single term. So let's do it to this one here too. So sine x, cosine x. Alright, sine x, cosine x. Alright, so now, this is going to give me, times that one, we got sine x, cosine x for that one. Alright, now y'all help me out with the other one. What's it going to result? Cosine squared, okay, because those would cancel there. Alright, and then another sine x, cosine x. Alright, and then up here the cosines cancel, so we get sine squared. Okay, now I'm looking at something here, and this you got like a similar question that's on the test. I remember grading this every year. Guess what people want to do there and they get it wrong? They want to cancel out. I mean, it's just like so tempting here. Sine x, cosine x. Oh, they're the same. Let's cancel them out. And then cosine squared over sine squared is cotangent squared. Yay. No. Okay. It's wrong. You can't do that because the operation is multiplication. Now, remember I told you two things. When you want to cancel out, think of one or two things. Either splitting, which is not going to work here because you got two terms in the denominator, or what's the other alternative? Factoring. Okay, so let's try to factor something. All right, in the numerator. You see anything we could like factor out there? A cosine. Okay, so we'll get cosine x times, all right, sine x plus, think about it, cosine times what would give me cosine squared? Cosine. Okay, cosine times cosine is cosine squared. All right, now what about in my denominator? A sine. Okay, so I've got two sines right there. All right, so when you want to cancel something, either split or factor. In this case, you couldn't split, so you had to factor. Right now, sine x times cosine x plus sine x. Now, you have to look really close, but there is something there that'll cancel. Yeah. Alright, sine plus cosine, and then cosine plus sine, are they not the same thing? They're just in a different order. Does the order matter when you add? No. Does it matter when you subtract? Yeah. So, I mean, if those were subtraction, we couldn't do that. But we can perfectly do this because now when we factored, what's the operation that makes this okay? It's multiplication. Now we're left with cosine over sine, which is, bam, cotangent. Okay. All right. See how these strategies start coming together here? Changing everything to sine and cosine, factoring, using Pythagorean identities. Okay. Splitting. All right. Now, this one kind of messed up, so we'll skip over that one. Javon did it, and then he said. So follow Javon on Twitter if you would like. Let me tell you my Twitter story before we do this one. Yes, I have a Twitter.
Oh my gosh.
All right, I have a nemesis on Twitter, and so my nemesis likes the Yankees. So by default, I like the Red Sox. Yeah, I know the result was not that good. Now, and so just to get at my nemesis, I follow the Red Sox on Twitter, and so anything positive about the Red Sox, and they tweet stuff all the time. I retweet. So, except for when they lose. That's a secret. I can't tell you that. All right. Now, so there's my Twitter story. All right, now let's do this one. Okay, so here we go. All right, no squares, no ones, Not very much multiplication. Maybe you could do this as multiplication of the reciprocal right there with something, but I wouldn't go there. Alright, so what do we do when we can't figure out anything? Change everything to sine and cosine. Okay, so here we go. This is already cosine. Alright, but now what about the cotangent? Yeah, cosine over sine. Alright, and then cosecant. 1 over sine. Now, somebody thought of this one a lot better, and I think you guys are going this direction in second period. 1 over cosecant is really just sine, isn't it? Alright, y'all want to go that direction? That's really smarter if you can spot that. Alright, so let's back up. Okay, somebody told me that in second period. I'm like, oh, they were so right. Okay, so we could just write that as sine. Alright, so that actually worked out pretty good right there. Now, but what do we have on my first term though? Complex fraction. Okay, now let's notice, is the entire expression a complex fraction? No, it's only the first part. Okay, now look at it. What would be the common denominator? Sine. So when I multiply by sine, am I going to have to multiply this one by sine? No, because it's not a part of the complex fractions. A lot of times what you get with complex fractions is you might get two separate ones instead of one big one. In this case, it's only just one of them here. So I'm going to multiply by sine. I probably should do it like right here. Okay, so now this will give me cosine theta, sine theta, over. Now let's see if y'all can tell me about the bottom part. It's just cosine theta. Okay? And we got plus sine theta. Now, y'all talk to me. Do y'all understand why we didn't multiply this one up here by sine? Yeah, it's not a part of the complex fraction. Okay? He's doing his own thing over there. So they need to multiply. Now, alright, y'all see something we can do from here? Yeah, cancel out. Now, that's legal because the operation is multiplication. Now, you're left with sine theta plus sine theta. Now, let me say this. Alright, some of y'all said sine squared. That's okay, I kind of expect that. But sine times sine would be sine squared. There you go, 2 sine theta. Think about it this way. X times x is x squared, but x plus x is 2x. So this would be 2 sine theta. Alright, let's look at one more and then I'm going to tell you something to start working on here. Alright, let's look at this one. Squares everywhere. Okay, but none of those really go together, do they? What? Sine squared goes with cosine squared, not tangent squared. Okay. Yeah, you could. Okay. Now, would that turn out nice if you changed tangent to sine squared over cosine squared? No. So, don't go there. Alright, I heard somebody say. Yeah, factor out sine squared. Okay. So this is a factoring thing. Alright, so what's going to tell us, hey, to factor instead of changing everything to sine and cosine? You have a common factor. See, when I see two things that are alike like that, I want to use a factoring strategy. So this will give me sine squared x times, right, what would be left here? 1 plus tangent squared. Okay, now that should look familiar. 1 plus tangent squared. I'm looking at a Pythagorean identity right there. What is 1 plus tangent squared? Secant squared. Okay. Remember, those are the ones you can write down. You can write down sine squared plus cosine squared equals 1 and derive the other two. That's one of the other two. So that is secant squared right there. So we'll get sine squared x times secant squared x. Now multiplying, what strategy works really good with just multiplication? Right, change everything to sine and cosine. So we get sine squared x times what? 1 over cosine squared x. Let's multiply that. Nothing cancels, does it? So this is multiply. This will give me sine squared x over cosine squared x, which is tangent squared x. All right, now look behind me. I'm writing down on my tablet so I can see my video on it here. All right, these on the board that are behind me. All right, these problems are going to use that strategy here. 1, 2, 6, 10, 11, 13, 14, and then 16 through 18. Yeah, I'm sorry, I should have clarified that. Yeah, the trig expressions 3 one, okay? Simplifying trig expressions 3. This is like the granddaddy worksheet because it starts putting every strategy together and it starts confusing us. Okay, it really does. So work hard on these. Look back at these examples. I tried to make the examples very, very similar, okay?